Hello, everybody. My name is Mateus Melchiades. I'm currently an undergraduate in computer science at the Universidade do Vale do Rio dos Sinos in São Paulo, Brazil. And I'm going to present my work, which is titled Anticipating Faults by Predicting Non-Linearity of Environment Variables with Neural Networks, a case study in semiconductor manufacturing. In a nutshell, the main problem we're trying to solve is the fact that while Industry 4.0 applications typically have dozens or even hundreds of sensors in their environments, which can give insights into processes, most of these insights generated are made through traditional mathematical models such as ARIMA. And we believe that we can improve this process by utilizing neural networks. However, work in this area is still fairly sparse. So our main goal here is to lay the ground for fault prediction in this sort of application using neural networks by mainly identifying behavior which is induced by the possible degradation by machines in a manufacturing process. So one of the main challenges we have currently is the fact that sensor data is often very unpredictable. So we propose a new metric, which we call Normalized Linear Offset, or NLO, which is basically the root mean square error of a linear prediction made from our original data applied to a rolling z-score. So as we can see in the equation on the right, we have the error, which is the real value highlighted in green by xk, minus the value estimated through linear prediction, which is highlighted in red and is the x hat. All of this inside a sum, which is determined by the number of windows we want to generate in the normalized linear offset. So this calculation is done by windows. And all of this turned into a root mean square. The neural network we are proposing is one that receives 60 data points as input, which is somewhat equivalent of 30 minutes of readings, and outputs the same amount of data predicting the future. This network is comprised of two LSTM layers, each of them with 240 neurons. Then a dense layer with unit 60, a dropout layer with rates 0.5, and then lastly, a dense layer with unit 60. This proposed network obtained the following results, as you can see in the image on the right. We trained the model for around 100 epochs with a dataset size of approximately 600,000 entries, which is equivalent to around a year of readings from our case study. We obtained a loss of around 0.437 and a mean absolute error of around 0.49. These results might not seem the most optimized. However, in our case, when we're dealing with environment sensors that can be unpredictable and a new metric, we can see that our layer has managed to detect all or almost all spikes in our test data, which is the goal of our project, mainly because these spikes are what determine when we have a great variation in our nonlinearity, which is what indicates possible faults in the sensors. So as a conclusion, we see that our model is fairly accurate and adequate for the situation because it can detect the spikes, which is the main objective of our work. As we can also conclude that the normalized linear offset, or the NLO, which we propose, it is able to circumvent the largest problem with the dataset, which is its unpredictability. And as a future work, we would like to adapt our model to train itself and evaluate these new trainings through transfer learning in a way that it can automate this process, especially because new patterns tend to appear in our dataset constantly in production, and new patterns often require retraining. So this is one of the main limitations we currently have, and we hope to work in the future. So thank you very much for your attention. And if you have any questions, I'd be more than happy to answer.